Hi, it's Kevin Joyce. This is the second in the series of the Gas Efficiency Masterclass on direct gas heating. The first section covered steam and hot water. Now we'll be looking at furnaces, kilns, ovens and dryers, which is where gas is used directly rather than creating steam and hot water. Similar to steam, you need to look at energy balances to see, well, okay, how efficient is the process? And again, the same thing applies if it's an oven or a kiln or a boiler, whatever it is. It's the fuel in versus the flue gas losses. And we show a steam one here, but the same thing is relevant for furnaces. And the energy in this case, not in water or steam, but into the product to do the work, to do the heat treatment or to do the process it needs to do. The difference, I guess, between furnaces and boilers is that most furnaces and ovens are a lot less efficient because of the higher temperatures or higher airflows than boilers. So there's a lot more potential in heat recovery for direct process uses normally than for the case with boilers. So how do we do these energy balances? Well, you measure airflows, or you can use various portable devices like pitot tubes and other devices to actually measure the velocity and temperatures of the flue. So that tells you how much energy in the air that's being exhausted from the process. The energy inputs, if you've got gas meters, obviously you can use those. You can use estimates from the burner ratings. You can do all sorts of things to get an idea of how much gas is going into the process in the first place. Clearly the process temperatures are normally measured, the mass of the material that you're trying to heat, the fuel conversions that you need to use to work out how many megajoules of energy go in and how many megajoules are lost. And then the flue losses, you're measuring the excess air, the flow and the temperature. So all of those inputs are used to work out what's called the mass balance, energy mass balance of the process. And from that you can identify the areas where you're losing most of it and whether there's any scope to improve that or reduce it. So what are the energy opportunities in direct processes? Again, complete combustion with minimum excess air. In heat treatment furnaces and ovens, it's very important to have proper heat distribution into the process. You have to operate at the right temperature. Some people operate their processes at a much higher temperature than they need to. And that can obviously waste a lot of energy because you're heating the air to a much higher temperature than you need to. Reducing heat losses from the chamber. A lot of processes you'll have leakage in the furnaces, so you'll have heat being carried out of the oven without doing any useful work. Air curtains in entrance and exits of the furnace and oven to stop waste heat spilling out of the furnace without doing its work. The draft, what are you running it at a negative pressure or a positive pressure? If you're running at too high a negative pressure, you can bring in low cold air, which you then have to heat up. And if you're running it at too high a pressure, you can have spillage out of the oven or kiln. We'll go into this in a bit detail with some examples later. But all of these things can impact how much energy you use per tonne of product you're producing. Optimum capacity utilisation. If you've got a big kiln and it's half full, you're heating a lot of air to not do any work. You really need to make sure that the process is fully loaded and fully utilised. Not unlike your fridge at home. If your fridge is half full of food and you've got a big empty fridge, you're using a lot of cooling to keep the food cool. That's no different in a big furnace or kiln. Waste heat from the flue gases. As I said to you before, with boilers it might be the temperature of the flue might be 200 degrees. Some of these heat treatment furnaces it can be 800 or 900 degrees. So the furnace may only be 30% efficient compared to 80% for a boiler. So if it's only 30% efficient, there's a lot more potential to recover all that heat that's being lost through the flue. Skin losses, again, the same thing applies at higher temperatures. The requirement for higher levels of insulation are needed. And certainly the use of better coatings like ceramic coatings and better refractories to reduce the losses are becoming very popular with higher temperature processes. Complete combustion, as I said, it's important to minimise the excess air because of the higher temperatures. The game is a lot different here because that air that's being carried out might be being carried out at 800 degrees rather than 200. So that's a large amount of energy lost to the system. And as I say, controlling that excess air, the fuel, monitoring the burner, controlling the burner efficiencies are all fairly critical in keeping the excess air levels down. Heat transfer. In all direct processes, basically you're transferring heat from the fuel, from the combusted fuel products, via radiation, convection or conduction. In most processes, it's a combination of these heat transfer mechanisms. In a bread oven, for example, it's mainly convection, where you're heating air and you're transferring the air across the bread to cook it. Whereas in a large heat treatment furnace, it's more radiation, where you're using radiated heat to transfer that to the metal. We said operate the temperature of a furnace at the right, if you can set the right temperature. Look, if you operate it at too high a temperature, you get more heat loss. Like we said, the process is at a higher temperature, the flue's at a higher temperature, so the losses are higher. You can create oxidation, say in metal processes. If you run at very high temperature, you can oxidise the metal and you create losses in the amount of metal that you're heat treating because you're oxidising it. Decarbonisation, you can create real problems with that. Refractory stresses, you can do all sorts of problems with running a thing at too high a temperature. So you really should look at trying to optimise the furnace temperature to still do the job, but at the required temperature, not excess levels. And clearly over the last few years, there's been a lot more work in automated control to eliminate human error. Reduce heat losses from openings. Look, a lot of furnaces and kilns, brick kilns and things will have holes in them so that you get air being sucked in or heat being pumped out. Basically, the thing there is to fix all those leaks so that the combustion can work effectively. If you can keep openings small, you seal any openings you don't need, and you open the furnace doors, particularly in batch furnaces, less frequently and for shorter periods. Obviously, if you've got a batch furnace and you open the door to take the product out and you leave it open, you get a hell of a lot of energy wasted before the next batch. You see in some furnace areas where people leave the doors open for an hour or so. If you just close the door, you'll keep the heat in the furnace for the next round. We talked about chamber pressure. Look, if you've got too high a pressure in the furnace, it can lead to leakage. If you've got too low a pressure, it can pull air in without taking place in combustion. It can pull air in through these leaks, and then that goes up as losses through the flue. Heat loss is only about 1% if appliance pressure is controlled properly, so it's important to do that. We talked about capacity. Clearly, optimum load of the furnace is important. Optimum residence time in the furnace, you need to plan that properly. All of those things you'd think would be common sense, but often people will not load the furnace properly and will not control the process as well as they should. Waste heat. I said that in high temperature processes, there's a lot of energy goes to the flue. So what do you do with that energy? Some people preheat the product. So if you're heating a metal or something, you can pass the exhaust products through and preheat the metal before it actually goes to the process. So that means that the gas burner doesn't have to heat it from ambient. Some people heat the combustion air. So if you've got air and gas mixing to burn, since if you've got hot air, so you've you recovered the heat and you're preheating the air to the burner, that obviously reduces the amount of fuel that you use because you've already preheated the air. You're not using gas to heat that air again. And you can use heat sources from other processes to do a low temperature application elsewhere. So all of those things should be considered now that gas prices have increased. So what are the high temperature saving opportunities? Well, good refractories, best insulation, planning furnace operating times, use of ceramic coatings. All of those things can save a significant amount of energy. Okay, so let's get down to some specifics. Ovens and kilns. This one here is a little batch heat treatment furnace that you'll see. On that furnace, there was massive temperature gradient because where the thermocouples that control the burners weren't located in the right place. You were overfiring the furnace to compensate. So by changing the location of the thermocouples, you weren't overheating the furnace, which led to all those things I mentioned before, the reduced energy and improved product. So improving the temperature gradient in this furnace, logging and profiling. So nowadays, most of the new instruments can log and profile the temperatures, and it'll give you a history of how well your furnace has performed. In the past, people were just flying blind. So that sort of not very expensive technology can help you fine-tune your piece of equipment. Exhaust flows, again, as I mentioned before, managing those. In drier processes, high temperature humidity probes can manage the amount of humidity. So in other words, they measure the humidity of the air and adjust the air-fuel ratios to compensate for that. That can save, 4 or 5% of the energy. And in a big process, that's significant. Some examples in brick kilns. Brick kilns are huge energy users. And the sorts of things are, some of these things might have 120, 200 burners on the top of the oven. This is an example of one here. You'll see on the slide on the right. That's a whole lot of burners. That's one section of the kiln. Kiln's probably 5 times that length. So there's a lot of energy and a lot of effort going into actually fine-tuning every one of those burners. So the maintenance guys goes and tweaks those burners to make sure they're operating as effectively as possible. All these big ovens or big kilns have gas meters. You'll see a pretty dusty one there on the left there. But they monitor that on a daily basis and they compare the gas that they use per tonne of product. And they carefully monitor to make sure that the furnace is operating effectively. So if the guys don't tune the burners and it starts to slip, the gas usage starts to go up compared to the tonnes of good product, then the management comes right on and say, well, let's get this thing right. Why does the energy go up and slip? Well, things like leakage. These things have kiln cars. The cars go through and they're sealed because they're very high temperature processor. At the bottom, those seals fail and there's leakage. So if you don't seal those correctly with sand, you'll get spillage out of the kiln and that starts wasting a lot of energy. As I said before, the burner systems are pretty basic, but they need to be kept tuned. Unlike a boiler, these things have to be tuned very regularly to make sure that they still are operating effectively. In that industry, I guess I can give you some numbers here that really show what the impact of high efficiency is. An old kiln will use about 3 gigajoules per tonne of gas, 3 gigajoules per tonne of useful product. A new kiln will use about half that. So they've done a hell of a lot of effort in fixing these things. So I guess the sorts of things they have in these kilns are waste heat recovery. So the basic kiln, even the energy inefficient one that was built 30 years ago, what happens is that they're a tunnel kiln. So the bricks come this way and the air flows this way through the kiln. There are 3 sections in the kiln there is a cooling section, a heating section, and a preheating section. So what happens is that air, the airflow, transfers. So what you're doing is that you're using the air, the cold air coming in through the exit of the kiln, basically to cool the bricks, which is what you want to do because you've done the work on the bricks. Then it goes through the firing section to do its useful work in firing. Now, because it's taken the heat out of the bricks, it's preheated. So that air is preheated when it moves into the heating zone, so you're using less gas. The exhaust air then flows out of the cooling zone, the entrance to the kiln, and it preheats the bricks coming in. So that airflow flowing counterflow to the bricks basically cools the bricks, preheats the air, and then finally preheats the bricks as it leaves. So a very simple process, but has a massive impact on the energy because it's replacing energy that you would need to cool and replacing energy you'd need to preheat the brick, and also you've got preheated air for combustion. So that's your basic situation. A new kiln now, because of scale and better control, is twice as efficient as one that was there 30 years ago, starting from that base. So it shows you how far they've got beyond that basic technology of using counterflow. So that industry is an example of how effectively you can use high efficiency applications, and they've been doing it for many years. Main reason because it's so energy intensive, it's a major input to their operating costs, and obviously as the gas price goes up, it's becoming even a bigger focus. Okay, heat recuperators on metal furnaces and those sort of things, the same principle. You basically got hot temperature air flowing out of the process, and you're using a heat exchanger to preheat gases for either combustion air preheating or for product preheating. So you've just got a heat exchanger in the exhaust, and that does the heating for preheating for the process. Again, that's becoming more and more popular as, again, the energy prices increase. A good recuperator should recover between 15 and 25% of the gas used on a furnace. This is an example of the metal industry. We've gone one step further. This is called a tower furnace, and this is for aluminium melting, so cylinder heads or engine blocks or things like that. What that basically does is that you put the billets or the metal that you want to melt into the top of the tower. You'll see this is a tower melter, and the exhaust products from the furnace counterflow across that. So as you feed the billets through, it preheats the metal through the exhaust. So it's taking heat out of the exhaust to preheat the metal before it flows into the furnace. So you can get massive improvements in efficiency there because you're basically preheating the aluminium before you then have to use energy to melt it. So, some of the larger foundries have these systems now. Typically 40% gas savings with something like that. Fairly capital intensive, but if you were to buy a new furnace, you'd probably go this way. I know the Japanese have been using these for many, many years because they've had very high gas prices. We've been talking about high temperature processes, kilns and ovens, furnaces and things. Let's talk about lower temperature processes now. Still direct, ovens and dryers. The potential is not as high because the temperatures might be 200 to 400 degrees C or something like that, the process. Still, however, you'll find a lot of processes running at much higher exhaust rates than they need to. So in other words, you're putting too much air through the thing. Not so much combustion air, but sort of process air. So if you can reduce those, or you can increase recirculation. So in other words, don't have all the heat go up to the exhaust. Recirculate some back through the oven. Waste heat exchangers to preheat incoming air again, you can use those. Improve temperature profiling in the oven so that again you only put as much heat in as you need to match the temperature treatment that you require. And then again, with these, say in milk dryers and those sorts of things, where you have high temperature humidity probes to minimise the amount of air you need to do the effective process. Again, a lot of people will commission these things based on the worst case, the worst humidity, the worst temperature condition, and no one touches them. So it might only be 10% of the time where you need to operate at that condition. So if you've got better temperature control and humidity measurement, you can make those adjustments to minimise the energy when the conditions allow that. Look, another example is clothes dryers. Big industrial clothes dryers use a lot of energy. And whilst most of them in this country have humidity control, if you look at your little domestic one at home, you'll have most of those have humidity sensors in them to minimise the amount of exhaust, believe it or not, a little electronic control system. But in the big industrial ones, they do that as well. So they measure the humidity, and if you're not over drying, you recirculate. So you're not pumping too much air out of the dryer, you're optimising it based on the dryness of the clothes during the batch. So at the start of the batch, it's very moist. As the clothes dry out, the humidity dries, so then the amount of waste heat is adjusted to compensate because you don't want to over dry the product. So that saves you energy. Some people go to the next stage of actually putting an air-to-air heat exchanger on the exhaust so that you've still got exhaust air going out. It goes through a heat exchanger, and through the other side of that heat exchanger, you're preheating the air that goes into the dryer. So that's the next stage in recovery for clothes dryers. Humidity, then heat recovery. Various other techniques where you can't have air-to-air heat exchanger, it costs you a lot in ducts and things. They have what's called a runaround coil, where you'll see in the picture there's two heat exchangers, and you run hot oil transfer from one coil to the other, so that if you're recovering heat from a process over there and you want to use it over here, rather than run large air ducts to transfer the energy, you can run hot oil or glycol to transfer the energy from the exhaust process to the incoming air. Another example, again, this is not new, but I guess the trend is for increased regeneration. In the milk industry and some of the other industries where you're pasteurising, what you're doing is you're taking cold milk from a tank, then you need to heat it, then you need to cool it down again. So if you did that without regeneration, you'd use a lot of energy to heat it and to cool it. So what they have is they have a series of one heat exchanger on a rack where they have a preheat section. So they configure it so that you're using the waste heat for preheating and the waste cool for pre-cooling, just on one rack. So you have three sections of heat exchange. The impact of that is new heat exchangers of that type are 90% of regeneration. So in other words, they're only using 10% of the heat and cooling that you would use if you had to heat and cool by having a regeneration section. Over the years, it used to be 70%, but now as energy prices go up, the amount of regeneration in the plate heat exchanger increases and increases as the energy prices go up, because you can justify the extra capital. Unfortunately, it's not a straight line. The more and more energy you try and recover, the bigger and bigger the heat exchanger. So it's a cost justification of how far do you go in recovering the heat against the gas and power prices. Process analysis, again, I mentioned processes. There's a whole lot of instruments, relatively low-cost instruments that can have a big impact on the performance. The top one there is quite a novel instrument that's been around a while. It's designed to run through bread ovens and pie ovens and things like that, so very high temperatures. The instrument is a data logger that measures temperature, but you put it in an insulated box and you send it through with your pies. So what you're trying to do is tune the furnace, a big long oven, so you can run it through and it measures the temperatures as it goes through. So you insert it into the pies, send it through, and you take the instrument out at the other end, and you can see the actual profile that has occurred during the thing. So then you can adjust the burners and send the insulated instrument back through the oven. Much better than feeding thermocouples, right through the oven and jamming up the oven. It just goes through. Hopefully it doesn't fry the instrument. If the oven breaks down and the instrument's in the middle, then it's a bit embarrassing. But they are a great instrument for fine tuning. Obviously you get better product, you save energy, and it's quite a simple thing to do these days. The bottom instrument there is the high temperature humidity instrument I spoke about. This is basically looking at humidity and changing the dryer conditions to suit the actual humidity. Because most dryers are set up for the worst condition. A lot of times the weather and ambient conditions aren't very high humidity, so in those times you can adjust the condition and save energy. Thank you. Sustainability Victoria supports business to take action on climate change and reduce energy costs. If you'd like to find out more about Sustainability Victoria's services, please visit them on their website.